I'm
This
one of the
conference will now be recorded.
Sorry, I just heard that. Yeah, I'm Mark Beutel. I'm one of the Northern Directors of the California Lake Management Society. We're a local chapter of NALMS, the North American Lake Management Society. And this is our third webinar of 2020. Thanks for joining. And keep your eyes out on our website, californialakes.org, for more of our webinars. You guys just heard that this webinar is being recorded. And yeah, I'm really honored to introduce you guys to Dr. Marc Beutel. Marc is an associate professor of environmental engineering at the School of Engineering at UC Merced. He earned a BS in civil and environmental engineering from UCLA and an MS in environmental engineering and a Ph.D. in civil and environmental engineering from UC Berkeley. His research focuses on sustainable management of dilute pollutions in the aquatic environment, including strategies to repress mercury bioaccumulation and internal nutrient loading in California reservoirs. Dr. Beutel has authored or co-authored over 60 publications in the topics of surface water quality, wastewater treatment, and mercury remediation. So please join me in welcoming Marc Beutel.
Well, great. Thank you, Mark, for that introduction. Honored to be here and give this CALMS webinar. Happy summer, at least the beginning of summer, to everyone out there, and I hope you're all hanging in there, staying healthy and safe during this crazy time. So yeah, the title of my talk is a review of managed nitrate addition to enhance surface water quality. Kind of might seem like an oxymoron, but we generally think of nitrate as a pollutant, and that'll be the beginning of the talk. But we also know nitrate as a strong oxidant. And with that characteristic comes some potential to manage biogeochemical processes, particularly at the sediment water interface of lakes and reservoirs. And so let's get into the presentation. The case study we'll talk about here, most of them are coming out of this review paper I wrote with a number of colleagues by the same title. This came out in 2016 in Critical Reviews in Environmental Science and Technology. So grab the paper, and if you're interested in wanting to understand some of these case studies in a bit more detail, check it out. Okay, so here's a presentation outline. Nitrate as a pollutant. Then we'll talk about biogeochemical linkages between nitrate and phosphate and nitrate and mercury. Then we'll look at case studies where nitrate addition has been used for phosphate control. Then we'll get into some case studies where nitrate addition has been used for mercury control. Then one case study of nitrate addition for sulfide control in tide flats, and then some conclusions. Keep in mind here, addition is sometimes on purpose, sometimes it's by accident. Sometimes we see unforeseen consequences of changes in wastewater treatment regimes. So it's not just we're adding nitrate on purpose, but there's been some interesting times where accidental things have happened that are informative, and we'll look at these case studies. So nitrate as a pollutant, we all know nitrate is a pollutant. Its addition or non-removal from the environment must be implemented thoughtfully. We know that there are a lot of hypoxic areas and coastal eutrophication areas throughout the world. Many of these are related to nitrogen runoff due to agricultural activity. And so we know nitrogen is not only a cause of eutrophication in coastal environments, but in lakes and reservoirs as well that are nitrogen limited or co-limited with phosphorus. Nitrate contamination in shallow groundwater is a big deal, and it's in the Central Valley where I'm teaching, but also in the center of the country as well. And basically, these red zones are underlying active agricultural areas with a lot of nitrogen fertilizer inputs. And then there's this strong linkage between human health and nitrate with the blue baby syndrome, where if the babies don't have the same enzymes to be able to manage the nitrate that adults do, and their ability to oxygenate is interfered, and the blue and blue baby is anoxia. So let's all acknowledge emphatically that nitrate is a pollutant in the environment. But there are these biogeochemical linkages between cycling of other compounds where nitrate may actually be of benefit when it's in the environment if it can be managed and input to the environment in such a way as to not to cause subsequent problems. So this is the classic redox tower. As we go down in redox potential in the environment, we get a different set of electron acceptors. We can imagine organic matter is donating electrons to these different tiers of electron acceptors, and these are microbially mediated transformations. And so if oxygen around, the aerobes make the most energy. If oxygen disappears and there's nitrate around, we start getting denitrifiers and manganese reducers, processing the organic matter and making a living. Once those electron acceptors are disappear, then you start getting into the more reduced microbes such as iron reducers, sulfate reducers, and methanogens. And the linkage here between iron reducers is once you get that reductive dissolution of this FeOH3. So that is a solid in the superficial sediments. Microbes reduce that to soluble Fe2+. Out comes your Fe2+ out of the sediments, and any phosphate that was sorbed to the original iron oxides also comes out. So there's this classic literature and evidence. There's a lot of other mechanisms that cause phosphate to come out of sediment. But one common one is if these iron oxides are reduced, out comes the Fe2+ dissolved and out comes the phosphate. And this is why you tend to see phosphate accumulate. It's one of the mechanisms that can cause phosphate accumulation down in the bottom of lakes. A more recently accepted or argued issue is this Fe2+. It's not a part of my review or a part of the case studies today, but there is growing evidence that it's not just this phosphate coming out, but it's this Fe2+ that may be a critical micronutrient for CHAB. C for cyanobacteria, HAB, harmful algal blooms. There's some interesting work coming out of Canada that is saying, yeah, there's a lot of nutrients around, warm temperatures, thermal stratification, but it's this potential internal loading of bioavailable Fe2+ that is really the trigger to set off some of these cyanobacteria harmful algal bloom. So there's the linkage between the iron cycle, right? If we get iron reduction, we get phosphate. Phosphate is a nutrient. You exacerbate your eutrophication. Now, with respect to the sulfate reducers, I guess I can use my pointer here. The sulfate reducers are implicated in methyl mercury production. Sulfate reducing bacteria kind of accidentally convert inorganic mercury to methyl mercury. Methyl mercury is the compound that is extremely toxic and bioaccumulates dramatically in aquatic food webs. So you can start seeing if we don't have oxygen or nitrate around, and we get into this redox scenario at the sediment water interface where iron reduction or sulfate reduction starts, well, we start seeing some problems. And so kind of the simple conceptual idea is, hey, if we have nitrate at the sediment water interface, we're going to poise the redox above the level at which iron reduction and sulfate reduction can occur, and we will not get this release of nutrients and toxins into the overlying water above the sediments, where it can then potentially diffuse or mix into surface waters. This is how you see it in action. This is data from Hodges Reservoir, a reservoir I've been working with the city of San Diego down in Southern California. And so this is 2017. What we're looking at here is depth in the reservoir and then time along the x-axis, January to November. And these are heat maps or isoplaths, kind of a topography map of water quality spatially and temporally in the system. And you can see this huge red anoxic zone. This is a hypereutrophic system. You can imagine as this oxygen is disappearing, the redox is going down, and we get this classic release of phosphate into the bottom waters. We also get this release of methyl mercury, and these are associated with the reduced conditions that are being experienced down in the bottom of the reservoir. And then we also have this immense productivity. This is a Mediterranean climate. There is no external nutrient loading during the summer. So this intense chlorophyll A is being supported by the internal loading of the phosphate, and the methyl mercury is also getting into the food web there. So we see this intimate connection between redox in the bottom water and the internal loading of these pollutants, which tie back to productivity in the surface water and contamination of the biota when we're talking about methyl mercury, which bioaccumulates in aquatic biota. So let's talk about some case studies here about nitrate addition for phosphate control. One of the early papers that really caught my attention on this topic came out of Germany, and check it out. It's a nice paper, Nitrogen Emissions into Freshwater Ecosystems. Is there a need for nitrate elimination in all wastewater treatment plants? So this paper put forth a simple conceptual model based on their observations in some kind of coastal or I don't think it was lake environments, but this could be a lake environment, but because that oxygen's going up and down, it's kind of more of a tidal or estuarine environment. So let's just walk through this conceptual model together, and it really encapsulates this idea of how nitrate can potentially be of benefit. All right, so we have time here, winter, spring, summer, fall along this x-axis. And the oxygen is okay in the winter and spring, and then things warm up and oxygen starts wobbling around here. We have nitrate around, presumably from discharges of treated nitrified wastewater, could also be runoff from agricultural activity. And you can see this nitrate is almost acting as a buffer here while the oxygenation is oscillating. You might have a period where you have no nitrate, it's been denitrified, the oxygen's low. And so now let's tie to the geochemical cycling of iron and phosphorus and sulfur. And so during these winter and springs when things are oxygenated, you have your iron in the Fe3 form, and it is a sink, absorption sink for phosphate. And so we have oxygen penetration into the sediments, we have nitrate penetrations into the sediments, and there's our kind of key keeper of the phosphate, right? It's absorbed to a solid form in the superficial layer. They're even arguing here in a way that phosphate dissolved in the water could diffuse into these sediments as a sink for phosphate, or perhaps it's particulate phosphorus depositing down. Now, as we go deeper, we start getting reduction of this FeOH, and the Fe2 then combines with sulfur to form some iron sulfide precipitates. Any phosphate that is liberated in this reduction and precipitation process is going to hit this iron oxide barrier and be sorbed. In this case, we're assuming there's plenty of iron in the sediments relative to the phosphate. Now, as we lose our oxygen, the nitrate hangs in there and keeps this kind of surface layer active. And then once we lose our oxygen and our nitrate, we get this reduction of the iron oxides to Fe2. I guess it would be kind of this process that's occurring. The Fe3 is going to Fe2, combining with S2 minus, forming these FeS precipitates. Out pops our phosphate, right? And then once we get reoxygenated, you start the cycle over again. But you could argue without this nitrate, this phosphate release would have started earlier. And in fact, one of the case studies I'm not presenting today, but is in the paper, is work I did at Lake Matthews, where down in Southern California, where this exactly happened down in the bottom of the reservoir. The oxygen disappeared, the nitrate hung in there, then the nitrate finally disappeared, and then you started seeing phosphate accumulation in the bottom of the reservoir. And if you did the mass balance calcs, I could show without that nitrate, internal release of the phosphate would have been 20 or 30% higher. All right, so let's look at this case study in Poland, which is a neat one. Ozerzuski Lake in Poland. Here's a couple of peer-reviewed articles you can go to, one from 2014, one from 2018. And the idea here is we've got this small lake in Poland. It's anaerobic, a lot of internal phosphorus recycling, and it's in an agricultural watershed, so it's getting a lot of external loading. Well, it turns out there's these two natural springs right near the lake. And check out this table of the spring water quality. The nitrate in these springs are on the order of 30 to 40 milligrams per liter. Right, so this is groundwater that's been contaminated due to agricultural nitrogen fertilizer inputs. And what they did is they captured the natural springs in a well and then got it down to the bottom of the reservoir to basically add an oxidant down there when there's no oxygen. And so let's look at, here's a picture of one of the streams being intercepted into this well. So really low tech approach here. And then they did a kind of presented some before and after data. So this plot up at the top here is the accumulation rate of phosphorus down in the hypolimnion of the lake. And you can see winter, spring, summer, when nitrate was not added, we're at 20 to 25 milligrams P per meter squared per day. And then in 2013, when they did their pilot study, you can see the internal accumulation of phosphate went down. And if we look down at the lower figure, these are profiles presented as bar charts from 0 down to 6 meters. For 2005, the no nitrate year, and 2013, the nitrate addition year. And this is concentration in the water. So you can see this concentration building up in the bottom under no nitrate conditions. And when they did add the nitrate, you can see in some cases the phosphorus was lower in the bottom water than the surface water. So they're still getting plenty of external nutrient loading, but it's a proof of concept effort, basically showing that enhancing the redox down in the bottom decreased phosphate accumulation. This same phenomena was shown in Occoquan Reservoir in Virginia. This is from Francisco Cubas and Tom Grizzard and others at the Occoquan Watershed Laboratory near Manassas. So the effects of nitrate input on water reclamation from a water reclamation facility on the Occoquan Reservoir water quality. So it's a big reservoir. It's kind of a run-of-the-river reservoir. And so we have these two tributaries coming in, and in Bull Run tributary, there's actually an advanced wastewater treatment facility that is putting in highly treated wastewater, reclaimed water into the reservoir. And that water is ultimately, along with the natural runoff, being used at a water treatment plant down here at the end of the reservoir. And it serves 2 million people drinking water. And this reclaimed water enhances the water yield of the system by 25%. So it's a great early example. This started in the 70s of indirect potable reuse of water. What's interesting is in the summertime, they save money in the plant by not denitrifying and adding nitrate-rich water to Bull Run, which then comes down into the reservoir and moves through the reservoir with time and actually poises the redox down in the bottom waters. One critical component to acknowledge here is by putting it in that tributary, it's added to cool water, and they've done the studies to show most of the water plunges down into that hypolimnion and gets denitrified as it finds its way to the dam. So this is an important part of getting the nitrate to the environment you want it in, where it's going to disappear from the environment. And so this is a data set of water quality from this, I think it's REO5, but it's one of the downstream sites. And so let's just take a look at it. Okay, we have time, and then we've got DO is the circle, nitrate is the square, and phosphate is the triangle. So we kind of see this classic, and this is in the bottom water, right? Bottom water of Occoquan Reservoir. And so we see the oxygen disappear at this site. And you can imagine this is a run of the river. There's water flowing through this site with time, and we're standing there just looking at the water quality. Oxygen goes down and the phosphate goes up. Right, so this classic deoxygenation of the bottom water, phosphate liberation from the sediments. Well, what happens in July, August is a pulse of nitrate finally makes it down to this site. And this is nitrate that would have come in from the treatment plant. And coincidental with that arrival of the nitrate, boom, you stop seeing this phosphate accumulation in the bottom water. The nitrate dissipates, we see a bit of phosphate, but then oxygenation comes back into the system and the phosphate decreases. So again, it's this really neat example of nitrate addition to the environment, kind of incidental in this case. Really, it's the water we want. But why treat the nitrate in the treatment plant when you can treat it in the reservoir naturally and get a kind of biogeochemical benefit of less phosphorus, internal phosphorus loading in the system? There's another case study from Denmark in Lake Ling. So good old Martin Sondergaard and his group. And this is hypolimnetic nitrate treatment to reduce internal phosphorus loading in a stratified lake. So in this case, you're actually adding it from a boat. Here's little Lake Ling, and there's sampling stations. It's about 7 meters deep, urban, kind of urban natural lake. I'm sure it gets recreational use, and a history of pollution, probably from a sewage treatment plant back in the 70s, then big algal blooms, and then folks trying to understand what to do, divert the wastewater, but there's still a lot of internal nutrient loading of that historical waste. And in this case, they added calcium nitrate. So what we have here is a time series of water quality. We have nitrate on top and dissolved inorganic phosphorus on the bottom. And the clear circles are at 5.5 meters and the dark circles at 6.5 meters. So both of these data points are deep down in the reservoir, right? So we're looking at the bottom water of the reservoir. Okay, so in 94, there's no nitrate treatment, and you get this classic accumulation in June, August, September of phosphate down in the bottom water. Okay, each arrow is a nitrate addition. You're cruising around in a small boat, dumping these I think it was solid calcium nitrate into the bottom of the lake. And we can see there's an immediate response of no phosphate buildup in the bottom or less. Same thing for the following year. And then it looks like they jacked up the nitrate a bit more. We're still at just a couple milligrams per liter, right? And you can see by the end of the season, it's all gone. So you're not polluting the surface water with nitrate. And then it seems like in the following 97, they didn't treat, but there was kind of a lag or an improvement that carried over from the previous 2 years. You probably oxidized a bunch of the sediment and made it a bit friendlier to retaining phosphate. So another interesting, compelling, small, we just saw a really large scale case study, and this is a small scale case study. Okay, I'll just check in and confirm you're all on board and can still hear me.
Yeah, we can hear you.
Excellent. It would be alarming if I didn't get a response. But yeah, good. I'm glad you're all there. Okay, nitrate addition for mercury control. All right, we did talk about this linkage between sulfate reducing bacteria and those bacteria being a critical component of forming this toxic methylmercury that then gets into the food web. So the idea here is if we can suppress the sulfate reducing bacteria, can we actually start seeing lower concentrations of methylmercury in the water? If the methylmercury is lower in the water, presumably it'll be lower in the food web. So this is a neat case study by David Austin, a consultant with Ch2M Hill. They're a new company now. Suppression of hypoammonetic methylmercury accumulation by liquid calcium nitrate amendment, redox dynamics and fate of nitrate. This is in NALMS, the NALMS journal, Lake and Reservoir Management. And so here we are in urban Minneapolis, Minnesota, right? The land of lakes. And so there's all these urban lakes. They're great recreational value. And it would be great if they could get delisted for mercury and people could actually fish. So the politicians, the people, there's a real desire to bring these urban lakes back to a more fishable condition. And so Dr. Austin and his team looked at 3 study lakes, Ann, Riley, and Round, and did a comprehensive field monitoring and basically showed a clear linkage that when these things stratify and go anoxic and the redox goes low, that's when you see the methylmercury in the bottom water. And they ultimately did a liquid calcium nitrate addition to Round Lake. So let's first look at this data set of, this is all the lakes before any nitrate addition, just trying to get a handle on, is there really a linkage between redox and methylmercury? And so I'm not sure if N is 7 samples or 7 seasons here. I'd have to go back to the paper. But the bottom line is they got enough data to really feel confident that it's at these low redox conditions when you see methylmercury in the lake water, while under aerobic conditions, you did not see that. So really what we're probably looking at is, summer and fall water quality versus winter and spring water quality. And so with this knowledge base, it's kind of common sense. Well, if we shift the redox up, will we see less methylmercury? So again, this was a proof of concept pilot study. And the idea here was to dump a couple truckfuls of calcium nitrate into this urban lake around Lake Minnesota and let the nitrate do its job and monitor the methylmercury dynamics. One interesting thing about the liquid calcium nitrate is it's heavier than water. So you can kind of not worry too much about, getting it in the exact place. It's going to find the exact place. It's going to sink down to the sediment water interface in the deep area and undergo denitrification. And so there's very little risk of the nitrate getting out into the environment. So this was a one-time slug dose. There's the truck pulling up. Check in with the homeowners association before you have the truck pull up, I suppose. But Dr. Austin said it was interesting. No one was too concerned. The truck just put a hose in there and they opened the spigot. Of course, they interfaced with regulators and got the appropriate permit and buy-off. So this is not a cavalier project by any means. But here's the data that we see. This is a heat map for the redox in the water. In this case, red is good, right? So reds, browns, and yellows is high redox. We're about down to 10 meters deep here. And here we see this little anoxic zone here going down to the, just starting to get down to that below 60 threshold where they started to see significant methyl mercury production. Boom, in comes the nitrate, and we can see for about 4 to 6 weeks, we're in the red zone, we're in the green zone, we're in the hundreds of millivolts. So the monitoring showed that the nitrate addition poised the redox, and then the nitrate disappeared and we got into significantly reduced conditions in the fall. And here's a time series of bottom water redox and methyl mercury. So this is methyl mercury and ORP in bottom water of Round Lake, Minnesota. The arrow notes where liquid calcium addition took place. All right, so the methyl mercury is still elevated, but not quite starting to totally accumulate. They put in the nitrate, up goes the ORP, down it comes as the nitrate is consumed. The nitrate disappears, out comes the methyl mercury, or really the production of methyl mercury is then, the window is opened here late in the fall. Good proof of concept. Of course, you would have wanted to maintain the nitrate down there all season and avoid this late season increase. Another interesting thing they hypothesized, or at least some of David's calculations showed, that the nitrate, rather than being oxidizing organic matter, it was actually oxidizing sulfidic compounds. And so in other words, as the nitrate was disappearing, you were actually building up a pool of sulfate. And so once the nitrate disappeared, you actually had really great conditions for sulfate reducers because of a lot of the sulfide had been oxidized to sulfate by the nitrate. And so you had the sulfide around, you then had low redox, and that's perfect conditions to get sulfate reduction and this methyl mercury increase. So, you got to be careful and anticipate some of these redox transformations that can work for you or against you. Whole lake nitrate addition for control of methyl mercury in mercury contaminated Onondaga Lake, New York. A shout out to any folks from New York, if you're on the line, or Virginia, or any of these places where we're talking about these case studies. This is the California Lake Management Society, but we love all of America, so thanks a lot for joining us outside of California. This is there's just tons of studies on Lake Onondaga by our colleagues from the Upstate Freshwater Institute. And so good old Onondaga, it's an urban lake, and it is just really super polluted with mercury. There was a chloralkali plant out on this end of the lake, and it's just extremely contaminated with mercury. So it's been a real challenge to manage. It's a big urban lake. It's a recreational resource. Check out here, you see Metro. You can see what this is, right? It's a wastewater treatment plant. So the wastewater for Syracuse is treated at this plant, and the water goes into the lake. It accounts for about 20% of the overall inflow to the lake. So huge footprint here from the wastewater treatment plant. So what happened? Well, Metro upgraded its treatment capacity to go, not capacity, but capability to remove some phosphorus, but also nitrify. So all of a sudden, or over a couple years, they stopped inputting ammonia-rich wastewater and started inputting nitrate-rich wastewater. And what do you think they saw? They saw nitrate, they saw phosphate and methyl mercury go down in the bottom of the reservoir because they're now treating the reservoir with nitrate. So we can look at that data set in a moment. And in some years, the nitrate would hang on. In other years, it would disappear. And when the nitrate disappeared, they'd see the methyl mercury and phosphate come out. So the idea was, let's do a pilot program and see if we can shave off these edges here and make sure there's nitrate down at the bottom of the reservoir all year round. We're really happy to have the nitrate from the treatment plant, but let's also see what the feasibility is of doing a barge treatment of nitrate on the reservoir. And so this is a schematic. This was Parsons Engineering and Freshwater Institute. A lot of collaborative work went on. And so the concept was to have the barge, have these tanks with liquid calcium nitrate, about 8% nitrate. In the end, you suck in the warm water. You mix it with the right amount of calcium nitrate to get a density when you discharge it, so it doesn't, the warm water is going to want to rise up, but you've now combined it with the nitrate and have a what they kind of called a neutrally buoyant or slightly negatively buoyant plume. And again, keep that nitrate down at the bottom, right? We don't want it up in the surface waters. We don't want it going out into the environment. We want to get that nitrate down where it's going to do its job to manage biogeochemical processes, but not eutrophy or pollute. And so we can look at a few pictures. Here's the barge, some mixing chambers, the tube going down to the diffuser. So, you know, really pretty modest infrastructure here. Probably you're renting the barge, so you're not really buying anything or installing anything near the lake. Same could go for pulling your truck up to the urban lake, right? No long-term infrastructure commitment. And here's the data set, the time series of maximum volume-weighted concentration in the hypolimnion. So it's a volume-weighted hypolimnion concentration of methyl mercury on the top and phosphorus, soluble reactive phosphorus orthophosphate on the bottom. So the clear circles are before the wastewater plant upgrades, and the upgrades included some phosphorus removal and nitrification. So now we start year-round nitrification, and with that nitrate, we see a drop in methyl mercury and soluble reactive phosphorus. But you can see some years are better than others. Some years are low, some years are high, and this is probably the nitrate kind of ran out towards the end of the season, and that caused some release. Once they started doing the nitrate pilot study, you can see they really reinforced the nitrate that was coming in from the treatment plant and dramatically, basically, you know, stopped the methyl mercury and SRP accumulation in the hypolimnion. So really interesting project. We could go into the whole issue of why did they use nitrate and not oxygen. I was on a team that proposed an oxygenation system, but the local crew there and the fact that nitrate was already working, and the fact that for oxygen addition, you commonly have something down on the lake bed where the oxygen is put in, the nitrate made more sense. But I did in one of my papers maybe it was in this review paper actually, I compared 1 liter of liquid oxygen, the oxidant content of that, to how much of the calcium nitrate solution that they would have to add to get the same oxidant power. And so 1 liter of liquid oxygen, so it's still not turned into a gas, so it'll go up to maybe 150 liters of gas. But that 1 liter of oxygen had the same oxidant content as 500 kilograms of their 8% calcium nitrate solution. right? So oxygen can hold, liquid oxygen can hold quite a bit of oxidant power. One thing to keep in mind, that's the benefit of oxygen, but one benefit of nitrate is you could actually really jack up the concentration of nitrate to hundreds of milligrams per liter. It's extremely soluble. So we tend to not want to do that in the environment because we're trying to minimize nitrate leakage. But you really could dramatically get a lot of nitrate down at a sediment water interface because of the solubility benefit of the salt. But anyway, really neat applied project there in Onondaga. This was not in the review, but it was a follow-up study I did at Occoquan Reservoir. We saw the previous talk or case study where we looked at phosphorus, and you might think, well, what's happening to the mercury, right? And so I did a study with my colleagues there, and we looked at what was really cool is we have a nitrate-rich tributary in Bull Run and a no nitrate tributary in Occoquan. So the real question is, how does RE30 compared to RE35 from a mercury perspective? And so here is some data for profiles for August 2013 at RE35. There's no nitrate, there's oxygen depletion in the bottom, and we see methyl mercury accumulation in the bottom. So the no nitrate Occoquan tributary. If we look at the nitrate rich Bull Run tributary, we see the nitrate down there in the cool bottom water, a bit of oxygen as well, and no methyl mercury. When the two come together, bit of nitrate, bit of oxygen, deeper still, no nitrate. So kind of a confirmation that where there was nitrate, there was not methyl mercury. For the sake of time, I'll bypass this data table, but it was just showing that, for example, in 2013, nitrate in RE35 is low, methyl mercury is 0.2 on average, but where we had 5 milligrams of nitrate, we had no methyl mercury, and there was statistical significance in that difference. So one last case study here, and we'll get to the conclusions. I had to throw this in for the sake of my colleague and advisor, Alex Horn. This was an early example of nitrate plowing in the tidal mud flats in San Francisco back in the late 70s. There's Dr. Marcy Cummings and Jim Roth, two colleagues of Dr. Horn out of UC Berkeley, and they're hand plowing calcium nitrate into the ground here. It's really a job for grad students, but I guess he talked his senior colleagues into helping. So the issue here is some biosolids, and some biosolids got spilled out into the mud flats, and all that organic matter led to enormous sulfate reduction and huge odor problem. So they did a little proof of concept experiment, and this is the total sulfide in the water running off of the mud flat, and then the days after the addition of the nitrate. The triangles are the treated little plot. It's a one-time treatment. Tidal water's coming back and forth, but it really had an effect over a month and a half relative to the non-tidal mud flats. And you can see 30, 40, 50 milligrams per liter of sulfide. That's a lot of sulfide. And some of that's going to be partitioning into the air as an odor. So there's another case study of this approach in the paper. So conclusions: nitrate is a pollutant, but also a potent oxidant. Nitrate can enhance water quality by regulating redox potential at the sediment water interface. When adding nitrate to anoxic surface waters, we want to add it close to the sediment water interface. We want to manage timing and magnitude so the nitrate is depleted prior to lake overturn. Don't want to add nitrate to end-limited systems, perhaps. But this is a really interesting issue for us to think about. Elimination of existing nitrate discharges may enhance internal phosphorus loading of mercury, internal phosphorus loading and mercury bioaccumulation. So don't think just eliminating nitrogen discharges from wastewater treatment plants is always a good thing. If it's in the form of nitrate and it's going to a unique environment where anoxia is resulting in internal loading and recycling of phosphate and methyl mercury, maybe we want that nitrate there. And in fact, removing it from the environment could exacerbate poor water quality. And finally, managers should look to couple existing nitrate discharges with hypolimnetic water bodies to economically improve surface water quality. So with that, let's chat. We've got a bit of time for questions. We can go back to some slides as needed. But yeah, comments and other experience you've had out there in the community, feel free to share those too.
Thanks, Mark.
Yeah, thanks a lot. That was sorry, Stephen, are you gonna?
Go ahead.
Cool. Yeah, thanks, Mark. That was a great talk. I'll be fielding questions through the chat feature. So if anybody has a question, please type it into the chat feature. I'm also posting a link right now to our post-webinar survey, so please fill that out if you can. And I'll start with a question from Stephen that was, is tracking nitrate and phosphate concentrations complicated by the fact that they're nutrients and that they're taken up and potentially transformed into organic forms? Perhaps focusing on the hypolimnion avoids that, but still the volume represented by the hypolimnion varies as the thermocline moves.
Yeah, no, for sure. It's not easy. I mean, we saw metrics like volumetric average concentration in the hypolimnion. The more shallow your lake is, the more it's tough to kind of think of the hypolimnion as its own kind of static environment. But yeah, there's challenges, but you know, it is kind of nice to be working down in that hypolimnion, and thermal stratification really can keep that fairly isolated. But I agree, you got to be careful with your mass balances. But if you think about it, possibly when you're looking at accumulation rates in the hypolimnion, those are underestimates of the accumulation, because you're probably losing some of those dissolved compounds to the metalimnion and epilimnion due to entrainment and diffusion. But yeah, definitely keep on our mass balance hats when we do this analysis. And, you know, I think what's really important is to do nutrient profiles and not just a bottom water sample, because that bottom water sample, when it goes down, did it go down because of enhanced mixing, or did it go down because there's really less mass in the hypolimnion? So good question, and that's some of my thoughts off the top of my head. Also, it's really good to track iron and manganese, I might add. Manganese in particular has been an interesting compound for me to track it relative to any type of redox management of your system, because manganese, unlike iron, doesn't reoxidize so easily. So if you see some manganese around, it really is an indication that at some point in the past, your water interface went anoxic, and maybe you didn't want that to occur.
Cool. Next we have one from Spencer, and it's for the run of the river reservoir, how is nitrate in the epilimnion managed or mitigated?
Yeah, you know, there's not much you can do. So the idea here is you saw 2 arrows, right? Not just the one down, but there is some nitrate into the surface. And so it isn't, in a way, it is potentially going to stimulate some algal productivity. But what, you know, this is folklore, at least at the site, is once they started getting some of that nitrate into the surface water, they saw less cyanobacteria. The idea there being that what nitrogen fixing cyanobacteria an advantage? No nitrogen around, right? They can get the phosphorus and then make their own nitrogen. Keep in mind, not all blue-greens are nitrogen fixers, but conceptually, if you add a bit of nitrogen to the surface water, you might not get a lot more algal productivity, because the nitrogen fixers were there using the phosphate and making their own nitrogen. Well, now instead of having that nitrogen fixed and getting a problematic toxic blue-green bloom, you're kind of adding the nitrate and giving green algae and other algae a chance to outcompete the cyanobacteria. And these algae tend to be less toxic, and they also tend to be of better food value. So now your zooplankton have something to eat, and off goes a more positive, robust food web. But yeah, I think it's a point. In this case, there was nitrate, some nitrate discharged to surface waters, but it didn't cause a water quality problem and may have actually enhanced or selected for less problematic algae species.
Okay, so next question, Byron Furman asks, how does nitrate compare economically to oxygenation for redox maintenance?
Yeah, good question. I had that, I shared those metrics on how much oxidant power is in liquid oxygen versus the calcium nitrate. I think it's less financial and more a practical matter. If you want a long-term, you're sure you want to enhance redox in your system, and it's a long-term project, I would go with oxygen. And you'd have some onshore facilities and some line diffuser or a cone down at the bottom where you inject the gaseous oxygen. If it's kind of a one-time thing or a small scale, maybe calcium nitrate is the way to go. I don't think in any formal cost comparison. So I think it really is site specific and depends on the kind of of the study. It seems like the liquid calcium nitrate is really amenable to these pilot tests, right? Pull your truck up, dump it in. Let's rent the barge and for a couple years and drop in the nitrate. That's a little harder to do with oxygen because you do need a bit more permanent infrastructure. But I mean, fundamentally, the benefit of oxygen, it's not a nutrient, not a pollutant. So that's where fundamentally oxygen is better than nitrate, right? Everyone wants oxygen. So I'd say oxygen is a real benefit from a regulatory perspective.
Cool. Alper Elsie asks or states, very interesting concept. I'm wondering if you're aware of any mathematical modeling studies that support the idea of nitrogen input.
Yeah, I mean, when you say mathematical modeling, does it mean of kind of the biogeochemistry at the sediment water interface, or more of a kind of water quality model? I don't necessarily. I'm not a modeler per se, but if you're thinking about things from a biogeochemical perspective, check out David Austin's paper and his Round Lake case study in Minnesota. He's kind of a redox geek and gets into some cool delta G calcs there. There was a modeling effort. Check out the review paper. Now that I think about it, in the conclusion area by the same Pretholz folks, the folks who I presented their conceptual model early on, they did a modeling study. And so check that out. And I think what they modeled was a lake that had nitrate coming into it, and they modeled how much more phosphorus and chlorophyll would they get if the nitrate was removed. So feel free to follow up with me by email or the paper, and that may get you headed in the right direction.
Yeah, I know some of the common models like the SQL W2 model have like sediment diagenesis features that most likely do incorporate these redox processes.
Yeah, and I think they're pretty simple. It's kind of might be if oxygen is there, you have one sediment phosphorus release rate. If it's gone, there's another one. You probably would have to maybe write in some special code to extend that. Maybe not, but yeah, I think it can be complex or simple, and that's modeling.
All right, looks like we have one more question and 2 minutes left, so I'm gonna go back to Spencer's other question, which was, what steps are normally taken when nitrate release from a wastewater treatment plant is near or above regulatory standards?
Yeah, I mean, good question. I mean, I'm not a regulator, but you know, if your lake is impacted and it's shown that nitrate loading is impacting a beneficial use of your system, there's potential for regulators to start saying, okay, the nitrate, this nitrate discharge needs to come down. If that's the Spencer in my wastewater class from last semester, we remember the TMDL, total maximum daily load approach. I think what comes to mind here is we've got to get away from thinking of things just in terms of nitrogen, right? Your question wasn't posed as a nitrogen loading question, but a nitrate loading question. What if that wasn't nitrate, but it was ammonia, right? And so for me, I'm thinking almost, rather than just thinking about nitrogen loading, we need to think about reduced nitrogen loading versus oxidized nitrogen loading, and acknowledge that ammonia is probably bad news, right? It's toxic, it's bioavailable, but nitrate might not necessarily be such bad news. Getting back to your question, what if the regulation total nitrogen thing you can't exceed? And that would cover both ammonia and nitrate, and yet nitrate was, like in the case of Onondaga Lake, having these ecosystem-wide benefits to the of lower phosphate removal, lower phosphate release, and methyl mercury release. So one take home from the study is, don't think of nitrogen loading, think of ammonia loading and nitrate loading, and move forward appropriately based on that.
All right, thanks. Looks like it's 1 o'clock, but we have one more question, so maybe we can just squeeze that one in. It's from Francisco Cubasauso.
Hey, Francisco.
Francisco says, where do you envision the nitrate research should go to avoid a halt in the use of nitrate to protect water quality, considering that nitrate is a pollution or a pollutant?
Yeah, and so that's Francisco Cubas. I presented his work there on Occoquan Reservoir, and I think many years ago, I don't know where it stands, but the advanced wastewater treatment plant was getting some attention from regulators down in the Potomac and the Chesapeake Bay, and folks were saying, hey, you got to lower your nitrogen discharges. And folks at the Occoquan lab were showing research where, hey, when it's in the form of nitrate, it can really be of benefit to the water quality in the reservoir. And we also get this ecosystem service nitrate removal rather than doing it in the treatment plant. As for future research, I think these case studies are really helpful. I think it's important to interface with regulators and appreciate regulators that have an open mind and can kind of understand that the fine point of nitrogen from the ammonia versus nitrate perspective. So I think we got to keep on with these case studies, and it would be really nice to understand where there are sources of nitrate-rich effluent and where there are impaired water bodies, and trying to bring those together potentially. Just a side note, I was reviewing the paper last night in preparation for this chat, and there is this interesting argument too about nitrous oxide production and nitrate discharge into the environment. You know, one knee-jerk reaction could be, well, we don't want the nitrate out in the environment because during denitrification, some of the nitrogen gas, some of the nitrate will go to N2O, not N2, nitrous oxide, potent greenhouse gas, and also the ozone layer destroyer. But I argued in the paper that actually denitrification down in the bottom of hypolimnium probably produces less N2O than discharging the nitrate to a terrestrial environment where there's more oxygen. You tend to get N2O produced when there's oxygen and the nitrate around, and denitrification is kind of struggling in a aerobic environment. But let's do more case studies. Let's keep working with the regulators and keep discussing within the reservoir management community this idea of nitrate being an oxidant, not just a pollutant.
Awesome. Well, yeah, thanks a lot, Mark. That was a great presentation. For anyone who's interested, I posted a link to the California Lakes or the CALM's website. The link to our webinars page is where we'll post the slides and the recording from this lecture. And yeah, please be sure to take the survey, post-webinar survey. I also posted the link to that in the chat. So yeah, with that, thanks a lot. And we hope to see you guys next time.
You guys, take care.
Thank you.